and welcome back. This still series is called Combinational Logic, but we're going to learn about Boolean Algebra that I've hinted about before. So I also mentioned a couple lectures ago that George Boole, Claude Shannon made the connection between transistors and the mathematical work of George Boole to, wow, ones and zeros and transistors and circuits. That connection was really wonderful and really rich, and so he named it Boolean Algebra in honor of George Boole. There are some primitive functions that Boolean Algebra has. They're and, or, and not. Powers are that we can use normal mathematics and connections between massaging things in the Boolean algebra world and then making a connection between how the circuit might change and be equivalent as well. This is the first thing I'm sharing that's brand new. From now on, if I ever say plus, I mean or. If I say times, I mean and. And if I draw a bar on top, I mean not. And if that bar is over a big expression, I mean invert that whole expression. If the bar is only over a term, I just mean invert that term. Okay, so remember that as we move on to this. So here is the Boolean algebra, here's the circuit of a majority function. What would that look like in Boolean algebra? Let's take a look. I'm seeing A and C, which remember now is A times C. I'm also seeing B times C. I'm also seeing A times C. And there's an or with all of that, which means they all have to be grouped with a plus between them. And that's what I get. A times B, A times C, and B times C. And you're going to notice, by the way, I didn't do the same order. The interesting thing is this order doesn't matter. Why? Because Boolean algebra tells us that addition is commutative. A or B is the same as B or A. And I can also flip the order of these two as well. A times B is equal to B times A because multiplication is also commutative. Pretty cool, okay? Because we know, when we kind of learning algebra maybe in 9th grade, we don't have to put a dot in between any two product. We can just say AB. Now remember, I don't mean AB, a single line called ab, and it's a single line called ac, and a single line called book. I don't mean that. I mean these are three different signals, and the products are themselves. This is a challenge when we go to the next slide, where you see that sometimes our input names aren't single letters. They're even more complicated. This input means it's a single signal. Let's try to say that 10 times fast. That happens to have 5 letters describing it. PS is a 2-bit signal, so I have to have PS sub 1 and PS sub 0. Again, this can be complicated, but let's see if we can actually work through this. We saw this before. Okay, this is our finite state machine encoded as a truth table, and it's a one only if and only if the first PS sub 1 is 1 and PS sub 0 is 0 and input is 1. So there's my circuit. We see this before, okay? We also saw we could simplify it into that. And the interesting thing is, how do I then take this and write this in a Boolean algebra way? Well, I've got PS sub 1 and, or times, not PS of 0 and input. So output should be the product of all three of those terms with a bar over PS of 0, and that's exactly what I get. Output is PS sub 1, one term, and not PS of 0 and input. Okay, and don't think this is 5 different inputs, each a single bit long, and it's I times N times P. That's not what we have. And so try not to have it. You could have a system where there's also an N and a P and a U, and that don't do that. Make sure you're very clear and don't ever have another bit input. Here's an I input and an N, and then some product is input, and that would be indistinguishable from this input, which is a single line, and you mean 5 different lines. Don't do that. So keep the naming consistent. You can get in trouble with that, so try just to be clean with that. We can do a simplification. This is our last slide on this, but we're gonna be able to see that I can go from a circuit to then some kind of equation derived from that circuit, and then use my Boolean algebra to actually simplify that circuit to get the simplified version. This is the simplest form of Boolean algebra. Therefore, I've simplified the actual circuits needed to. So if I'm gonna have to wire these guys or use transistors on a chip, I would much rather have the simplified version. That's the fewest number of transistors to use that. This is only one gate. I love that. That's much better than these 3 gates. This has much more delay. This has more area on a chip, have more delays. There's a lot of reasons I don't like this more complicated circuit. I do want the simplest form, fewer delays, all of that. So we're going to see the power of Boolean algebra is this. And the next slide, the next lecture is going to be all talking about what are these identities we're doing to massage these equations down. They look like, they look like normal. Look. AB plus A, somehow I distribute like an A out to get B plus 1. How is B plus 1, 1? We're going to show you all of those rules in the next lecture. We'll see you there. There's just one more thing before I close. I almost forgot to mention this. One of the great ideas about Boolean algebra is that I can say, I got 2 circuits. Are they the same or not? Actually, if I use Boolean algebra to simplify both circuits, so convert the circuits to the Boolean algebraic equivalent, then massage them down to see if at the core they end up at the same simpler equation. If they're the same simpler equation, they are the same circuit. So it's a great way to be able to see if 2 different circuits that look very, very different are actually the same thing. Once I use my Boolean algebra to simplify them to the simplest form, I can just compare those simplest forms. It's often hard to kind of figure out what the simplest form is if you kind of just have measure fewest gates or something, but it's really a nice way to be able to compare 2 different circuits. Just want to make sure I added that before I closed. Thanks.